Okay, we just talked about the basic functions of the transformer. Let me give you a few uses for the transformer. So one use for the transformer is to step up or step down the current. This is essentially what PG&E does. They have very high voltage lines and then they step them down and bring them into your house. And so you could have some input signal that has a peak voltage of 1.3 volts here. You could put a 10 turn to a 5 turn transformer, which will act like a step down, so the voltage across the secondary should be half the voltage across the primary, and that's shown here. So instead of a 3-volt peak signal, we have a 1.5-volt peak signal. Okay, that's one use. Another one is to isolate ground. You can imagine having an AC signal with a DC offset. So essentially there's some DC component or some average value, so we're oscillating here around 5 volts. We could input that into a secondary coil or into a transformer, and what we'd see on the secondary, we wouldn't see anything that has to do with the DC part, right? Because that DC part doesn't produce the changing magnetic field, it produces the flux that produces the EMF in the secondary, and so we just sense the AC part. And so this is actually what is in your oscilloscope when you do a AC coupling, right? So this, they essentially put a transformer in between the input and the output so that you only sense the AC piece. And the third use is sort of as an impedance matching bridge. So if you imagine you had some circuit where it had an input impedance of 400 ohms, but our load was 4, and what you really wanted was to match the impedance so that you had maximum power dissipated by the load, you could imagine hooking up a transformer that had the right number of turn ratios that would make that 4 ohm into a 400 ohm impedance. And so you could essentially match the power dissipated to the load in that fashion. So those are some uses for the transformer. So let's think about we're going to use some transformers in the lab. And so essentially we're going to hook up PG&E, 60 hertz signal, VRMS 120 volts, which means a peak voltage of 170 volts. And we're going to hook it up to a transformer. Typically the 100 turns to 10. We're going to step it down so that it's safer. And so we're going to step it down by a factor of 10. So the VRMS is going to be 12 volts and the peak voltage is going to be 17 volts. And so what are we going to measure? So typically this transformer has 3 outputs. There is 2 outputs at either end or 2 connections at either end, and there's typically a center tap right here. And so what are we going to measure? So imagine you take your scope and you hook it up to the outer leads. What are you going to measure? Well, you're going to measure the AC signal that has a peak voltage of 17 volts, as shown over here. Okay, because essentially what happens is this side is always going to be 17 volts higher or lower than this side, or the varying function of that. Okay, so what happens if we measure the scope from the center tap to one of the leads? Well, in that case, if we put the center tap here, that grounds that point, what we're going to measure is really only half the voltage. So we're going to measure a peak voltage of 8.5 volts, right, in phase. But what happens if we center tap, ground the center tap, measure from there relative to that point, and we're going to measure on channel 1 what we just measured before? Well, as we'd expect, we get the same thing, but we put channel 2 on the lower end of this the secondary coil. Well, then we're going to get a signal that has the same frequency, half the voltage, but it's going to be out of phase. Okay, because in the end, no matter what we call 0, the difference between the outer taps has to be whatever the signal is. In this case, it's 17 volts at the maximum point. Right, so we need 17 volts or whatever we read right here across each of those leads. And so what we measure, though, is relative to ground. So we're getting half of it here and the other half here. So they end up being out of phase.